Let's talk about monoids. Monoids are a wonderful pattern, abstraction, that once you know about it, it crops up pretty much all over the place. And every time you spot one, it brings a little smile to your face. Because quite often you sit and struggle with some complicated code and there's some friction and you just can't get things quite to sort of fit. And you have this feeling that something is slightly off. And then you suddenly see, oh, you have a monoid. Or you see that you need a monoid and you fix your code and then voila, all the friction is gone and everything just turns into this simple, beautiful code that will do exactly what you want in a general way. Now, what are monoids? The word monoid is just a word. It comes from the mathematical literature, and it's Greek, and it comes from the word mono, which means one, and oid, which means, well, I don't know, oid. If Microsoft invented these things, they would be probably called appendable. So monoids are things that can be appended somehow, but there are some rules to them. And strictly speaking, mathematically, these are algebraic structures which consist of a set, some combination operator, which I will just call plus, and an identity element, a neutral element, which I will call E. And then we have some rules for these things. So the rule number one is closure. And that simply states that when I pick two elements out of this set A and combine them using this operator here, the resulting element also needs to be in A. That's closure. Two, we require that this plus operator is associative, which simply is saying that it doesn't matter when you are combining more than once which order you do things. So A plus B plus C can either be A plus B plus C, and that should be identical to A plus B plus C. And that's a useful property, as we will see later, when we talk, especially when we talk about the monoid homomorphisms. And the third thing is that we have a neutral element, which we call identity, which sort of acts as a 0 or a 1 in this monoid. Now, this last requirement is sometimes kind of hard to achieve. And if you don't have that, so if this one is missing, then you actually have something which is mathematically called a semi-group. But that's now you've heard it, and if you ever come up with that, you can go and read the literature about what you can do with semi-groups. So let's do some examples, because this is all awfully abstract, and monoids are, believe me, simple things. So let's look around for some monoids. So the first one we're going to look at is, I'm going to take the set of integers. I'm going to take normal plus, and then we're going to have to find a neutral element. And I'm just going to guess here and say, well, 0. So let's see, is this a monoid? If I add two integers, I get an integer. There's no way of adding two integers and get a floating point number or a string or an object or something, unless you're doing JavaScript. So yeah, so closure, check. Is addition associative? Well, yeah, addition is associative, so check. And then the neutral element. If I do 1 plus 0, I get 1, which is the identity. So yeah, check. So this is definitely a monoid. So let's check another one. Int, and this time let's use multiplication. And this time I'm going to say that the neutral element is going to be 1 for integers. So 2 integers multiplied is an integer. Yes, check, we have closure. Is multiplication associative? Sure. That's check. And then I can multiply whatever number by 1 and I get the same number back. So we have identity. So yes, this is definitely a monoid. How about division? Int, divide, and then what element should we choose? Probably 1. We'll just guess here. Okay, so integer divided by integer, is that an integer? Can be, but not necessarily. So 1 divided by 2 is definitely not an integer, and there goes our closure. That's a float or a real number, so this is not a monoid under division. So we see that this is really important when we are dealing with monoids, is that we really look at what is the data we have, what is the sort of set we have, and what is the operation, and depending on we have different identity elements. So here the identity element was 1, under this operation here it's 0. So we need to just keep these things sort of straight in our head. So what about floating point, which would do real division and 1.0? Because we already know that anything divided by 1 is just going to be the same thing, right? So is this a monoid? Well, I can do 2 real numbers, divide them by each other, and it's certainly a real number. So yeah, closure, check. But how about associativity? If I say 5 divided by 4 divided by 2, or we should say 0, 0, 0. If I do 5 divided by 4 divided by 2, is that the same as 5 divided by 4 divided by 4 divided by 2? No. So that's then associativity breaks. So not a monoid. A very common monoid that we encounter often is the string. So I'm just going to say string. The set of all possible strings. I'm just going to use plus here. Some languages use plus plus and some languages use other operators. But I'm just going to say plus, and the neutral element is just going to be the empty string. So if I add 2 strings, I get a string. So we have closure. If I say Jonas plus Euserius plus exclamation mark, it doesn't matter which order I do this. Both will produce the same. So it's associative for sure. And if I add empty string to whatever string, I always get the same string back. Thus, this is a monoid. So list, just any list of whatever elements. Again, I'm just going to use plus here for the operation, and the neutral element will be the empty list. It's kind of obvious that the list will be a monoid. But now let's look at another slightly more involved example. Our friend option. Is option a monoid? Can I add 2 options? So we would say option of some type A plus, and what should the neutral element be? I'm just going to conjecture that it's going to be nothing. And then we'll check it. There's a little thing, but let's look at this. How we could say just I'm just going to define this plus operator for this option. So I'm going to take a x and a y. These are both options. And then we can say, okay, let's see. Match x comma y with. Okay, so what are the possible cases that we can have with this? Two options. I can have sum x, sum, oh, I should, well, I'll just call it A, and sum B. Right? So I have two options. And I need to make an option, since I need the closure, so I can't do anything else. I need to produce an option. So what should this be? Well, this should be sum A plus B. But I actually hadn't said anything about these things here. And here I'm adding them up. So there's an additional requirement on this. And this gets, in F#, unfortunately, somewhat technical. It's much easier to do in Haskell. But one needs to require that the A's here are restricted so that the A's are monoids themselves. So we need to require that this is a monoid, whatever type we put in there. So if we do an option of int, we're all good. Option of strings, all good. Option of list, we're all good. And as we will see later in a little while, there's always a way we can work around this using something called the free monoid. So just now assuming that these things here are monoidal, then I can just add them up and wrap them in sum. So now we have added two option values. Then we have some A, nothing. What should that be? Well, there's not much to add here, so we just return sum A. And there you see how nothing suddenly is working like this neutral element, because if I add that to this, nothing happens. And then we have, of course, the nothing sum B to sum B. And of course, the last one is the nothing clause, which is just nothing. So there you go. So now we have actually implemented sort of a monoidal add for the option type. And we can see that option is indeed a monoid, and we can easily implement the monoid for it under the constraint that whatever the monoid, whatever it contains actually is a monoid as well. Right. So why are these things so useful? How can they help us? Well, quite often we can do an example. We can start with just a normal list fold. It doesn't matter if it's a list or something, but a fold, and see how we can actually, using monoidal properties, we can simplify these things, because folds are kind of complicated. So we have a left fold, a fold. We know that a fold takes a function of two arguments. So typically it would be something like fun, and there's an accumulator and an element from some list, and then it does something. And then we have an initial value, which I will just call I, and then we have a list of elements. So this is the sort of normal way a fold is set up. Now, what if I know that this is a monoid, and I just want to just continue using the monoidal properties. Well, then I can actually already know something about that thing. Because I know there is a neutral element, which in this case would be an empty list. So I don't have to give it. So now we can just turn that, by just knowing that fact, we can just turn this into list reduce. And now I'm just going to say here, add a plus function, which is a function of two variables, of course, and it will just combine whatever I give it. So now I can say reduce 1, 2, 3. And now I know that since I have now given a list of integers, the neutral element will be automatically 0. Since that's the neutral element for this list, and now I'm using the fact that I have a monoid list of monoids, and I'm combining them. Also know that the order doesn't really matter because it's associative. So now I've simplified fold by just knowing the fact that I can use the monoidal properties of integers. Now I can simplify this further because I already know, since I know that these are monoids, and I know how I want to combine integers, I can actually get rid of the plus. I can do sum 1, 2, 3. Now, and that's pretty cool. So that will sum up these things. I will get 6. But what if I had a list of lists? How would that look then? Now, I know that the list is a monoid, right? Then I couldn't do this, could I? Well, sure, because if it's a monoid, it has a combination operator, and in fact it has a neutral element, which is the empty list. And yeah, then we can just do it. And then I could just say something like this: some list of 1, 2, 3, 4, and the answer of from this would be 1, 2, 3, 4. So that's a way of flattening a list using the monoidal properties, which is quite neat, and everything just falls out of this. Alternatively, I could have written this as dot reduce, and then in real F# has this list combination list append operator at. So I could have done list reduce at and then given it a list. So that's a little bit about the sort of closure. Since we know that given a certain type integers, we have to produce an integer. Given lists, we have to produce a list, and so on. So we can actually deduce quite a lot of information already from that fact. Associativity I will talk about in the next lecture when we talk about the monoid homomorphisms. But one of the things that associativity gains us, if we know that we have it, is that we know that we can do things either one way or the other. We can do A plus B plus C, or we can do A plus B plus C. And this is quite useful in sort of divide and conquer schemes where you can split data up partition it into chunks and then add it later. Which can be a very efficient way of computing things, in particular in parallel. And yeah, of course, we already saw the usefulness of this neutral element. The neutral element is kind of nice because what happens often is that you are doing some kind of algorithm, and then the lack of a neutral element is making you put in a lot of special cases into your code. So you are going to have if some condition, then do this, otherwise do this. And often if you look at it carefully, if you would have a neutral element, you could just say, well, okay, then empty or identity element, and nothing will happen. So you can just, you know, pass the empty list or nothing. And that can sort of help make much clearer and nicer code. So let's do a little case study. I see that I'm my markers are getting pretty poor. So let's see if we can find a slightly better marker. Let's see. Yeah, there's more juice in that. Okay, so let's do an example of some sort of semi-real, slightly contrived, not perfect by any means example. But suppose now that we have a we're doing some sort of business system. We're doing some order management thing, and we have some type which I'm going to call order line, which is a record type, and it has some code. This is the product code. It's a string. It has a quantity, int, and it has a price, unit price, which is a float. Right. So now you can say, oh, okay, I'm going to order 5 food bars, each costing $5. That's our order line. Now, suppose now we want to sort of add up all the orders, and we want to add them. So we start by adding 2 orders. So how could we do this? Well, naively we just go let add orders, order A and order B, and then the question is, what should this return? Well, maybe we want just to have some intermediate representation of things, so maybe we should have this return an order. So let's see what would happen. Well, what should the code be when we add 2 orders? We have a code there. Well, code, I don't know, maybe we can just mark it as somehow special. So we're just going to say this is the total so far. Quantity, well, that's easy. We can just add A quantity plus B quantity. But that's probably not a very good idea either. Because what if I like have 26 nails and an ice cream? The quantity doesn't really make any sense. That's combining different units. There's apples and pears getting smashed into one thing, so that's not good. The only thing that really makes any sense to add is the price, which we could say just A price times A the quantity plus B price plus times B quantity. But this is not really good. Like, if you would implement things like this, you would get smacked on your fingers. Now the question is, how can we somehow turn this into something which adds up normally and naturally and monoidally? And the answer is, well, yeah. And this is a trick that we can do very easily. We can pretty much turn anything into a monoid for free. And actually it has a name, it's called a free monoid. And it's exceedingly simple. And the way it works is like this. Instead of having a code being a string, I'm just going to say string list, since list is a monoid. And quantity here is going to be an integer list. So for just normal product order lines, these things will just be a list with one element in it. Not so nice, but hey. Now this whole thing has become a monoid, because I can just add strings, add lists, and add quantities, and then add the price. at each step. So now I have something which is really sort of properly monoidal, and I can have some kind of sensible way of adding them easily. But of course it's not really how you should do it. So we could do another attempt at this, and albeit this is a little bit contrived, but it sort of shows the purpose of this. So what we can do is we're going to say, well, okay, we're going to have the order line. It's going to be some kind of product code. It's going to be a quantity. It's going to be a price. And then we're going to say, okay, define order as, or either it's a product of order line, or it's a total of float, or it's empty. And this is important here, because that is our neutral element that we're going to need. And now I can implement for this thing static methods. And this is actually, there's a little bit of internal F# magic going on when we do this. But I can implement two static methods on this. So I can just go width, and then I'm just going to continue up here. Static method 0 with a capital Z equals empty. So I'm just going to use the last case. And I can create a static method plus A comma B, and then I can do pattern matching on these A's and B's. A, B, with, and then I can match up sort of product, and produce a total. Or I can do product total to produce a total, or I can do total product and produce a total, or I can do all the different cases of this. And if I do this for these products, these order lines, I now created a proper monoid of this thing. And now I can actually do things in F#, and this is real code. I can actually say list sum, and then I can give a list of these order lines, O1, O2, order type objects, and I will get out a total with some number in it. So that's pretty neat. But the most useful property of monoids, usually when we are programming, is that once you realize you have one, and you know that it's associative, and you have the neutral element and closure, it allows us to really clean up code in a nice way. Suddenly, the tricky bit became much easier. So that was monoids. And next lecture will be on the monoid homomorphism, which is just a little extension of this. It's going to be a very short lecture. And then, yeah, then we'll turn our attention to more patterns, more abstractions.